Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is 9.4, which is comparison of series. Alright, so there's many series that do not follow the form that we've learned so far, right? So for example, we know that if I had this series of 1 over 2 to the n, right? This is a geometric series. But if I have a series of 1 over n over 2 to the n, well, this is not geometric, right? Similarly, if I had something like 1 over n cubed, this is a p-series. But if I had something like 1 over n cubed plus 1, this is not a p-series, right? So the idea here is that, well, there's functions, there's series that kind of look like a series that we already know, but they're not exactly that. So how do we figure out what they're doing, right? Are they convergent or divergent? How do we tell? Well, we have two kinds of comparison tests that we're going to talk about here. So first, let's talk about the direct comparison test. And this is what the direct comparison test says. It says um, let 0 be less than or equal to a sub n, which is less than or equal to b sub n, right? For all n. Now, if the series of b sub n converges, then the series for a sub n also converges. Right? So look at what we're talking about here. If we have a sub n, the sequence of a sub n being less than the sequence of b sub n, and we know that the series that's associated with b sub n, if that one converges, then the smaller a sub n, the series associated with a sub n, also converges. Similarly, if the series associated with a sub n diverges, then the series associated with b sub n also diverges. All right, so essentially here what we're saying is, if we know that some series converges, then a smaller series, right, a sub n being smaller, would also converge. If we know that a series diverges, then a bigger series, right, a sub n being smaller than b sub n, so b sub n being bigger, then that series would also diverge. All right, so in here, I want to make a note about these comparisons. Comparisons must make sense. All right, so if a large, so you don't want to like say that, like, for example, if the larger converges, then the smaller converges, right? That's true. Similarly, if the smaller series diverges, then the larger series also diverges. But if we have something that diverge and we're comparing it to something that's smaller than it, well, that's not helpful, right? Similarly, if we had something that converged and we were trying to figure out something that was going on with a bigger series, it wouldn't help. It wouldn't be helpful. So let's take a look at some examples, right? So again, with series, the instructions are always determine if it converges or diverges. So let's look at this series. So the series from 1 to infinity of 1 over 9 plus 2 to the n, right? 9 here, well, let's consider the following. So consider this. We know that 2 to the n is less than 2 to the n plus 9, right? Because I'm adding 9. Adding 9 is always going to be bigger. So if I divide both sides, so essentially if I do like a cross division, I end up with this, right? So what we're saying here is that this is useful because the series from 1 to infinity of 1 over 2 to the n plus 9 is going to be less than the series of 1 over 2 to the n when we go from 1 to infinity, right? And in here, well, this over here, and I should be going from 0 to infinity. Why am I going from 0 to infinity? Because I'm working with a geometric series, all right? And here I can rewrite this um, as 1/2 to the n, right? And that's clearly geometric. And because it's a geometric series, well, we know that this converges, right? It converges by a geometric series. And here are r, which is 1/2, right? It's less than 1. So it definitely converges. This implies now, by the direct comparison test, so this implies that the series that we care about of 1 over 2 to the n plus 9 converges by direct comparison test, right? Remember, we always want to say what test we were using when we figured out whether it converged or diverged. All right, so let's look at another one. Let's say that I have the series of 1 over the square root of n cubed plus 1, right? And in here, well, let's consider the following. We know that n cubed is less than n cubed plus 1, right? So that tells us the square root of n cubed will be less than the square root of n cubed plus 1, right? And at that point, we can clearly say that if I divide both sides here, they can do like a cross division again. I end up with 1 over the square root of n cubed plus 1 being less than 1 over the square root of n cubed. And we care about this because now we have this series being compared to this other series, right? And well, we know what this one's doing. How do we know? This is a p-series, right? And here I can rewrite this as the summation from n equals 1 to infinity of 1 over n to the 3/2, which this converges by p-series, right? Which tells us now that the series that we're interested in also converges. It converges by the direct comparison test. Right? So in general here with these comparison tests, we kind of have to really know what the series that we're comparing it to, what it's doing. Excuse me. So now let's look at this one. Let's say that we had the series from 1 to infinity of e to the negative n squared. All right. Well, let's look at this. Let's do this one at a time. Well, one step at a time. If I take a look at n is less than n squared for n being greater than, well, let's do this. N is less than or equal to n squared for n being greater than or equal to 1, right? So throughout our entire domain here, from 1 to infinity, this is true. So how is that helpful? Well, that tells us now that if I take the negative of all of this, right? So that's going to tell me that negative n squared is um, less than or equal to negative n, right? Because I negated everything. Perhaps I should write it this way. Negative n is greater than or equal to negative n squared. All right. And now I can rewrite it this way. So remember, when we multiply an inequality by a negative, we have to change the sign. We have to reverse it. So this is I'm gonna rewrite it now as negative n squared is less than or equal to negative n. And if I exponentiate both sides, I end up with e to the negative n squared is less than or equal to e to the negative n. Which again, we want that because now we can say that the summation from 1 to infinity of e to the negative n squared would be less than or equal to the summation from 1 to infinity of e to the negative n, right? And now what do we do with that? Well, let's look at that series. The series from n equals 1 to infinity of e to the negative n would be the same thing as saying the series from n equals 1 to infinity of 1 over e to the n, which this is geometric. And we know here that the ratio, the common ratio that we care about, that r in this case, would be the absolute value of 1 over e, and that's definitely less than 1, right? And it's bigger than 0. E is 2.718, so 1 divided by 2.718, definitely less than 1. So this tells us that this converges, right? And the one that we cared about was smaller than a converging. So this is geometric and converges. So what we know now is that the one that we really cared about, e to the negative n squared, also converges by direct comparison. All right. Next one. D. Let's look at the summation from n equals 1 to infinity of cosine of n plus 2 over the square root of n. All right. So let's do some side work here because this is gonna take considering what's happening up here. Let's consider cosine of theta, right? And I guess I can use n. Cosine of n. In general, the range of cosine is between -1 and 1. But I'm not interested in cosine of n. I'm interested in cosine of n plus 2. So if I add 2 to everything, -1 plus 2, 1. 1 plus 2, 3. Right? And then if I divide everything by that square root of n, well, that's 1 over radical n over radical n over radical n. I don't really care about that 3 over radical n. What I care about is this comparison that we're doing here. Because now what we can say is that the series of 1 over the square root of n, from n going from 1 to infinity, is less than the series that we care about, right? And why do we care about that? Because now this one over here, this one is a p-series. It's a p-series with p being equal to 1/2, which tells us it diverges, right? Because remember, with the p-series test, anything between 0 and 1, any exponent between 0 and 1 definitely diverges. So this tells us now that the series that we cared about, cosine of n plus 2 over radical n, diverges. All right. So diverges by direct comparison. All right, next one. Let's look at the following. E. Let's look at the summation from n equals 1 to infinity of 1 over 2 plus radical n. All right. And well, let's look at this. We know that radical n is less than radical n plus 2, right? Doing that cross division again, I end up with 1 over radical n plus 2 being less than 1 over radical n. And in here, well, what I have is a series from n equals 1 to infinity of 1 over, alright, it's 2 plus radical n, just so that I have what I started with on this side. And that's going to be less than the series from n equals 1 to infinity of 1 over radical n. But this right here is not helpful. Why is this not helpful? This diverges by p-series, right? We saw that in the previous example as well. This diverges by p-series. But the series that I'm concerned about is a smaller one. All right. If you recall from the very beginning, I said that the comparisons must make sense. I mean, this comparison does make sense overall. We're comparing radical n with radical n, right? That's fine. But this one happens to diverge, and this one over here is a smaller one. It's a smaller series. So what do we do? So how do we take care of this? Well, we're gonna come back to this problem because I want to talk about the next comparison test first. All right. So the next comparison test is called the limit comparison test. All right. So limit comparison test. And the limit comparison test is as follows. If we have the series a sub n being greater than 0 and the series b sub n being greater than 0, and if I take the limit of the ratios, right, of a sub n over b sub n, and that equals L, where L is finite and positive, and L is greater than 0, finite and positive, all right? Where L is finite and positive, then a sub n, the series of a sub n, and the series associated with b sub n both behave similarly. What do I mean by that? That means that either both converge or both diverge. All right. So let's go back to this example over here. So E. So we had the series from n equals 1 to infinity of 1 over 2 plus radical n. And all right, so now in here, I want to compare with the series from n equals 1 to infinity of 1 over radical n, right, n to the 1/2. We know what that does. It diverges, right? It diverges by p-series. So let's figure out what this one does. Now, since this one diverges, we kind of have a feeling that this one should diverge too, but we need to prove it. So let's take the limit as n goes to infinity of the ratio of the two. Now, it doesn't matter which one you call a sub n and which one you call b sub n. That part's irrelevant, all right? So you can put this one on top as a numerator, and this is the denominator, or the other way around, all right? In this case, I'll use our original as our numerator. And what I'm comparing it with, I'll use it as our denominator. All right, so in here, I've got a fraction being divided by another fraction. And we know that when that happens, it's the same thing as just multiplying by the reciprocal, right? And in here, well, what is that going to do? Well, we end up with the limit as n goes to infinity of radical n over 2 plus radical n. Well, we have n going to infinity. What we can do here is we can multiply both the top and bottom by 1 over radical n, right? Essentially, this allows us to cancel some stuff out here, right? Remember that multiplying by 1 is a thing, right? And here in yellow, that fraction is just 1. So what do we get now? So we get the limit as n goes to infinity of 1 over 2 over radical n plus 1. And as n goes to infinity, this goes to 0, so I get the limit overall is 1. 1 is positive, 1 is finite. So because it's positive and finite, that tells us that both series behave the same way, right? And since with this one was diverging, well, the other series, the one that we really care about, must diverge. So 1 over 2 plus radical n diverges by limit comparison test, right? And notice that's the limit comparison test because, well, we already know about the direct comparison test, so those are two different comparison tests. There's another one. F. Let's say that I had the series of 1 over 5n plus 7, all right? Now in here, what can I compare this to? All right, whenever you're thinking about what you want to compare it to, essentially think about get rid of all the constants and any constant being multiplied into a variable. So what I'm going to do here is I'm going to compare with 1 over n, all right? We know what this one does. This is the harmonic series, right? And we know that this diverges. And you can think of it as the harmonic series or p series where p is equal to 1, so therefore it diverges. All right, so now let's see what this is going to do. So we're going to take the limit as n goes to infinity of the ratio of the two. I'll do the one that we're comparing it with as the numerator this time, just so you see that it has absolutely no bearing which one you choose. All right, so at this point we're going to say we have a fraction divided by another fraction. So that's the same as multiplying by the reciprocal, right? So I'm going to multiply by 5n plus 7 over 1. And, well, what happens when I distribute that 1 over n here, right? Because these ones are not doing anything. So I end up with the limit as n goes to infinity of 5 plus 7 over n. And as n goes to infinity, that goes to 0. The 7 over n goes to 0. So overall, this limit is just 5. And 5 is positive. 5 is finite. So that tells us that both series behave the same way. And this one over here, well, excuse me, the one that we were comparing it with, we already know that it diverges. So that tells us now that the one that we cared about, 1 over 5n plus 7, diverges by limit comparison test. All right. Next one. G. Let's say that I had the series of 1 over 3n squared minus 4n plus 5. All right. Now, in here, whenever you have like something like this that kind of looks like a polynomial there, you want to just keep the highest exponent there. All right. And again, you want to get rid of everything else. You want to get rid of this 3, the 5 as a constant, and we're going to get rid of that minus 4n as well, because it's a smaller degree than this one. Overall, this n squared is really what's doing the driving force of this. So I'm going to compare this with 1 over n squared. we know what this one does, right? This is a p-series. So this one converges by p-series where p is equal to 2, right? Remember, with p-series, p being strictly greater than 1, it means that it's going to converge. So now I'm going to take the limit as n goes to infinity of, I'll do it this way again, 1 over n squared over 1 over 3n squared minus 4n plus 5. And at that point, what does that give us? Well, divided by a fraction means multiplied by the reciprocal. So I have 1 over n squared times 3n squared minus 4n plus 5. Distributing that 1 over n squared, well, that gives me the limit as n goes to infinity of 3 minus 4 over n plus 5 over n squared. And as n goes to infinity, that goes to 0, that goes to 0. Overall, our limit goes to 3. So because our limit, that 3 is finite, it's also positive. So because we got a positive and finite limit, that means that both of the series that we were working with behave the same way, right? So now we can say that the series of 1 over 3n squared minus 4n plus 5 converges by limit comparison test. Limit comparison test. All right. There's another one. Let's say that I have the series of radical n over 2n squared plus 7. All right. Remember how I said to come up with a comparison. I said ignore pretty much all the constants, right? We don't want to ignore the square root of n on top, even though I did say to look at just that highest degree. We don't want to ignore the top though. So essentially, what we want to do is get rid of everything, right? Like for example, actually let's do it this way. I could even add an 8 there, all right? We want to get rid of so same rules for top and bottom. Get rid of all the constants and just keep the highest degree. So I'm going to compare with the series of radical n over n squared, right? This can be reduced, right? Because radical n is just n to the 1/2. So this is really the series of 1 over n to the 3/2, right? And this converges by p-series, right? Where p is, in this case, 3/2. And 3/2 is bigger than 1, so it definitely converges by p-series here. So now, let's take the limit of the ratio of these two. So the limit as n goes to infinity, and I'll take 1 over n to the 3/2 over radical n plus 8 over 2n squared plus 7, right? And at this point, well, what does that give us? Well, let's see. We're going to end up with the limit as n goes to infinity. We're divided by a fraction, so it's the same as multiplying by the reciprocal. So I have 2n squared plus 7 over radical n plus 8, right? And at that point, let's distribute that n to the 3/2 into everything here. So I end up with the limit as n goes to infinity of 2n squared plus 7, right? 1 times that. And at the bottom, n to the 3/2 times the square root of n, that's n squared. N to the 3/2 times 8, that's 8n to the 3/2. At that point, well, we know that we can multiply it by 1. And from Calc 1, you should recall how to do this limit. Multiply by 1 over n squared over 1 over n squared. Because now what we get is the limit as n goes to infinity of 2 plus 7 over n squared over 1 plus 8 over the square root of n, right? And as n goes to infinity, well, 7 over n squared goes to 0, and n over the square root of n, 8 over the square root of n, excuse me, also goes to 0. So we end up with 2. And at that point, well, 2 is finite, 2 is greater than 0. So now we know that both behave the same exact way, right? Both series behave the same exact way. So now we can say that the series that we originally cared about, which again was radical n plus 8 over 2n squared plus 7, converges, right? Because the one that we were comparing it to converged. And these both behave the same way. So this one converges by limit comparison test. All right. Cool. Next one. All right. So let's say that I had something like the series of 2 to the n times n squared over 9n to the fourth plus 1. All right. So what am I going to compare it to? So let's see. Let's look at how I'm going to look at this. So compare with the series of, well, actually I shouldn't be going from 0. I should be starting at 1 in both of these. I'm going to compare this to 2 to the n times n squared over just n to the fourth. So essentially I got rid of that 9 and the 1. Now in here we can reduce this, right? This is the same thing as saying the series of 2 to the n over n squared, right? This n squared on top and then to the fourth on the bottom, reduce. Now, what does this do? So if we if we actually look at this sequence, all right, so this is going to be some side work to figure out what this is doing. If I look at the limit as n goes to infinity of just this sequence, 2 to the n over n squared, right? Well, in here, what does this go to? Well, we have infinity over infinity. Well, we can't really look at that. So this is infinity over infinity, which we can't do. So what we want to do is, let's look at the function version of this. The limit as x goes to infinity of 2 to the x over x squared. Well, by L'Hopital's rule, what we can say here is that this is the limit as x goes to infinity of 2 to the x times ln of 2 over 2x. Now this is still infinity over infinity, so what we can do is apply L'Hopital's rule again, and what we end up with here is the limit as x goes to infinity of 2 to the x times ln of 2 times ln of 2, and all of this over 2. 2 to the x, there we go. And as x goes to infinity, well, now we end up with infinity, right? On the bottom, it's just 2, so we have infinity over 2. Well, infinity times ln of 2 times ln of 2, well, that's still just infinity. And then over 2 is still just infinity. So because what we have here, we've got our sequence, it is not going to 0. And if you recall from the nth term test for divergence, this tells us that if the sequence doesn't go to 0, then the series must diverge. So this is a divergent series. So let's see how that applies with this one. All right. Let's do the limit comparison test now. So we're going to take the limit as n goes to infinity of the ratio of the two that we have. And I've got, what was it? 2 to the n over n squared over 2 to the n times n squared over 9n to the fourth plus 1. And what do we have here? We have a fraction being divided by another fraction. So we know that really means multiply by the reciprocal. So I have 2 to the n over n squared times 9n to the fourth plus 1 over 2 to the n times n squared. At that point, what do we see? Well, we see here that n squared and 2 to the n and 2 to the n cancel each other out. N squared times n squared, that can be combined. So what do we get? Limit as n goes to infinity of 9n to the fourth plus 1 over n to the fourth. If I split this up as two different fractions, well, what does that give me? That gives me the limit as n goes to infinity of 9 plus 1 over n to the fourth. As n goes to infinity, 1 over n to the fourth goes to 0. So overall, this goes to 9. 9 is finite, 9 is positive, so that tells us that both of the series behave the same way. So, well, that's going to tell us that the series that we cared about, going from 1 to infinity of 2 to the n times n squared over 9n to the fourth plus 1, diverges, right? It diverges because what we were comparing it to was also divergent, right? So it diverges by limit comparison test. All right, that is the end of 9.4, the limit comparison test. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.